Thank you all for attending the Innovations in Networking Awards luncheon. Every year we enjoy the opportunity to highlight members of our community who are doing extraordinary and innovative work. As I present the award, I'll provide a summary of each project and ask the team members present to come up and receive their award trophy. This afternoon, immediately following the presentation of awards, there'll be a general presentation session where the awardees will discuss their award-winning work. I'd encourage you all, if possible, to attend this session. We'll break a little bit with that tradition because we have one group of awardees who obviously are not present with us at the meeting, but are present via video conferencing, and we'll be talking with them in just a little bit. The first award on the list goes to Sonny McPeak and the California Emerging Technology Fund. Sonny has served as the president and CEO of the California Emerging Technology Fund since 2006. This nonprofit organization is working to close the digital divide in California by accelerating the deployment and adoption of broadband services to underserved and unserved communities and populations throughout the state. Under Sonny's leadership, CETF has enhanced California's efforts in closing the digital divide with groundbreaking projects and programs such as the California Telehealth Network, digital literacy, smart housing policy, school to home, and Get Connected. The CETF does truly remarkable work in assisting with broadband adoption in California, and CETF has been a great partner of CNIC's over the years. Please join me in congratulating Sonny McPeak, the California Emerging Technology Fund, her chairman, Michael Peavy, secretary, Barbara O'Connor, and Treasurer Rich Mata. Thank you all very much for the work that you do. And we have a lovely award for you that we could hold up to the screen, but I don't know it would do much good. Sherilyn's going to hold it up so you can see it.
Where you're at, but
Okay. Very nice. So Sonny and company, we'll turn this to you.
Thank you, Louis. Thank you very much, and welcome everybody at CNIC to the conference. I'm here with Chairman Michael Peavy. He is chairman of our board of directors. He's also the president of the California Public Utilities Commission. And we are delighted to be a partner with CNIC, and this is a special award. I was there with some of my directors from CETF 6 years ago at the CNIC conference, and we were just getting going. We had the benefit of listening to CNIC, to having a discussion about how we work together, and indeed I think it's been a great partnership over these years. Of course, we want to applaud CNIC, who has been a pioneer in advancing high-speed internet access to connect all the research institutions, to be a voice for connecting all education facilities, and to be a partner now with working with a couple of the regional consortia that are funded through the California Advanced Services Fund. I want to actually turn to our chair, Michael Peavy, because in California, the Public Utilities Commission absolutely was visionary and trailblazing when they, in 2005, directed that the California Emerging Technology Fund be established. And since then, there's been a very purposeful, conscientious effort of a number of us to work together, including CNIC as a trailblazer as well, to set goals and then to just systematically work towards those goals. I'm going to talk a little bit more about that, but I think it would be very fitting if you heard from our chairman and the president of the PUC first, who had this vision and who has made sure that everybody in California is now working together and working from the same strategic plan. So ladies and gentlemen, Chairman of the California Emerging Technology Fund, Michael OBrien.
Well, thank you, Sonny. You're most kind in the words you say. The Public Utilities Commission, in cooperation, frankly, with AT&T and Verizon, created the California Emerging Technology Fund to close the digital divide in California. We've been at it for 6 years now. Ms. McPeak is the president, the executive, the chief executive officer, the heads of the staff. It's headquartered in San Francisco with an office in Los Angeles for Southern California. And I think we made tremendous strides when we began this effort to close the digital divide, to increase broadband application across California. We were at about the same place as the United States as a whole. Now we're many, many steps ahead of the country as a whole in terms of advanced broadband. It's a great pleasure to work with her, with the entire staff, with the whole program. And the Public Utilities Commission, we have expanded this program. We created something called the California Advanced Services Fund to help those that help basically incentivize communities and that have little broadband or don't have any. And now the legislature has created the California Broadband Council. So this state has made a tremendous investment in developing and developing and expanding this whole infrastructure in broadband. And it's very fitting that this award go not just only to the California Emerging Technology Fund, but to its president, Sonny McPeak, because the leadership she has shown in this has been really quite incredible. With that, Sonny, it's just great to work with you and your entire staff and all the leadership that you've provided.
Thank you so much, Mike. And can I just maybe say a few more words, Louis? To all of you there with CNEAC, we want to underscore how important your visionary work has been. You've been in existence long before the California Emerging Technology Fund, and you're going to continue after we have concluded our work. We have seed capital of $60 million, and we have taken that a sizable sum, but against a state as large as California, trying to figure out how do we actually leverage it to achieve two big goals. One is 98% deployment in a decade, that is getting to 98% of all residences, all households, to have access to high-speed internet service. And then on the adoption side, that we achieve 80% adoption, that is 80% of all Californians in their homes will actually have the benefit of using broadband, of subscribing to it. When we began in 2007 and started measuring where were we, it was about 96% deployment, and we said in order to achieve that goal of 98%, we were going to have to connect another about 500,000 homes that were spread out over 44,000 square miles, and that territory is the size of the state of Kentucky. We've been really grateful to the work that CNEAC has done in figuring out how to use your resources and the infrastructure that CNEAC has to be part of that base from which we can achieve that goal. Even more challenging when we looked at all of the data was what we had to overcome to get to 80% adoption. And most sobering was the fact that low-income households in 2007 were only at 33%, Latino families were at 34% adoption, and people with disabilities were at 36%. Today, those three very vulnerable populations that have a low adoption have come up to about 60%, and in order to achieve our goal in the next 5 years, it's another 880,000 households that need to get connected. These big goals that are a shared vision only get accomplished when we work together. And when we have had the benefit of working with Jim Delganis in the past and the team of CNEAC, and you now, Louis, to think through very creatively, as we had the benefit of discussing a month or so ago, what can CNEAC do in working with the tribal lands? What is it that the universities can help us with innovation do? You're there at Cali T2 with with Dr. Larry Smart and Jerry Sheehan, we envisioned that the innovation that's represented by your audience can help us tackle this public purpose challenge of getting California connected. It was CNIC who was the first to say a gigabit. A gigabit is what we want to do in California to have world-class speeds. We want you to continue to advance that vision and put California back in the world leadership role that we once had and need to continue to strive for and to innovate towards. We are in Sacramento, unfortunately, this week, and not with you in San Diego because it's sort of broadband week in the capital. And we apologize for not being there in person, but appreciate being able to use the technology. Tomorrow, Chairman Peavy will chair the California Broadband Council, and the Broadband Council will consider a policy of integrating technology into all education in California, K-12 as well as higher education. That's the kind of policy milestones that we are beginning to achieve, and much of that is because CNIC has laid the foundation in California. I want to conclude by saying we will be very honored to continue to be your partner. We take this award as an obligation as much as a recognition of our work, an obligation to continue to achieve those goals, and we thank you for your commitment and dedication to closing the digital divide in California.
Sonny and your staff at the CETF and your board, along with Chairman Peavy, thank you so much for all that you do. It is an honor and a joy to work with you, and we look forward to sharing and working towards our common vision.
Thank you, Louis. Thank you.
Thank you.
And it was kind of cool to use the technology, too. In the category of educational applications, the award this year goes to iLabs, the Remote Online Lab Network. iLabs Remote Online Labs enable students to use real experimental devices via a web browser. Online laboratories, iLabs, are experimental facilities that can be accessed through the internet, allowing students and educators to carry out experiments from anywhere at any time. The Center for Educational Computing Initiatives at the Massachusetts Institute of Technology and the Northwestern University's Office of STEM Education Partnerships jointly offer a number of opportunities through the iLabs network. These include the ability to experience the excitement and authenticity of using high-end equipment to investigate the world in the same way that scientists do. More flexibility in where and when labs are performed, before and after class, at home, in study hall, and without time limits. Access to costly or delicate lab equipment otherwise not available. New economic models and public-private partnerships for provisioning lab equipment. As of November 1st, 2012, nearly 5,000 students have used the iLabs network, averaging about 139 experiments a month. From 2011 to 2012, the Remote Online Labs network has grown by 74% and includes a number of CNIC-connected schools, colleges, and universities. It's truly a remarkable effort that MIT and the STEM initiative partnership have made. We're very happy that it benefits California in the way that it does. And I'd like to have you join me in congratulating Kemi, Jona, and the iLabs team. I guess we'll do this afterwards.
Wait, yeah. You want to put it back and we'll sure. California stuff.
In the category of high-performance research applications, University of California, Santa Cruz Cancer Genomics Hub. UC Santa Cruz has built CGHUB, a 5 petabyte database to store tumor genomes that that will be sequenced through National Cancer Institute projects. Through this effort, CGHUB is tackling the significant computational challenges posed by storing, serving, and interpreting cancer genomics data. The CGHUB mission is to facilitate the work of scientific researchers. It's designed to be a fully automated resource, appearing to the user as an extension of the user's home institute computing system. Of course, making such vast amounts of data accessible to collaborating researchers nationally and internationally requires advanced networking such as that provided by CENIC to allow the research to be carried out seamlessly as seamlessly as possible. The project is led by UC Santa Cruz bioinformatics expert David Hassler. Hassler is a distinguished professor of biomolecular engineering in the Baskin School of Engineering at UC Santa Cruz and a Howard Hughes Medical Institute investigator. Please join me in congratulating the CGHUB team in the category. Please join me in congratulating the CGHUB team. Is there anybody from? Yes. Yes. Thank you.
Thanks a lot. We really love it.
This is actually one of the for those of us at Scenic, it's a great event to be able to see the amazing things that people do with the network. It's very inspiring. In the category of experimental developmental applications, Project Adamant. Workflows, especially data-driven workflows and workflow ensembles, are becoming a centerpiece of modern computational science. However, scientists lack the tools that integrate the operation of workflow-driven science applications on top of dynamic infrastructures that link campus, institutional, and national resources into connected arrangements targeted at solving specific problems. Project Adamant, adaptive, data-aware, multi-domain application network topologies, uses two successful software tools to solve these problems. The software tools employed are Pegasus Workflow Management System and Orca Resource Control Framework. The integration of Pegasus and Orca enables powerful application-driven and data-driven virtual topology embedding into multiple institutional and national substrates, providers of cyber resources like computation, storage, and networks. Project Adamant leverages ExoGenie and NSF-funded Genie testbed, as well as 3 national research and education networks, National Lambda Rail, Internet2, and ESNet, and existing OSG computational resources to create elastic, isolated environments to execute complex distributed tasks. This approach improves the performance of these applications, and by explicitly including data movement planning into the application workflow, enables new unique capabilities for distributed data-driven big science applications. Project Adamant is a collaborative effort of the University of Southern California Information Sciences Institute and RENCI UNC Chapel Hill and Duke University. Please join me in congratulating Ewa Dielman of USC and the Project Adamant team. And Sherilyn is accepting on behalf of Ewa.
But they will be coming in via video conference for the presentation.
Yes, they will be coming in. And Ewa was here last week when we had the 100 gig workshop in conjunction with On Vector and gave a tremendous presentation. Lastly, I think I will turn the mic over to David Reese, Vice President Scenic.
Thank you. It's my distinct pleasure and honor to introduce the winner of the Individual Contribution Award. Many of you here, I think, can remember Scenic in the early, late 1900s when it was an idea, there was a concept that we could all work together, and you know, the C in Scenic didn't stand for corporation that time. It didn't exist. It was maybe collaboration, consortium, you know, pick your definition of the letter. Another phrase I think many of us know of that generation is the one, it takes a village. And truly, I think that describes Scenic in those days. It had no staff, no employees, and took a great many contributions of the villagers. And among those, there are some that stand out over time. And this year's winner, Ken Lindahl, is one of those who stood out as clearly one of the leaders. Many of us know him as, Mr. Multicast or Mr. Network Guy, as his business card said. One of the quiet ones, which simply led by, doing and demonstrating how one could bring the community along and do some things. With that, I'd like to also call up on some of the other villagers that lived and worked with Ken to describe what it was like in those times and give you another flavor of Ken Lindahl. So, John Haskins, I understand you're one of our, maybe John doesn't know. We can deal with that later, John, but your name is on my paper. So as a villager, I welcome you to the podium.
Well, I once upon a time worked for a community college, and in about 1998, I took a job at UC Santa Barbara, and immediately I got tossed into going to these meetings with the new organization, Scenic, that was being pulled together. I noticed this guy that was at the meetings that had a real smooth voice, and he talked and generally seemed to make sense. I was about 14 at the time, and Ken really helped me a lot in figuring out what it meant to do networking for a campus. And I was impressed that he was able to collaborate really well, not just with the other UC folks, but with as the years went by and other segments became part of Scenic with the K-12s and the community colleges, and he even put up with the folks from Stanford. So thanks, Ken. I really appreciated your presence all through the development of Scenic, and even still, now that you've moved on to better things.
So next we're going to head south, and we're going to hear some words from Mike Van Norman from UCLA on. And Ken, I'm sorry, but I'm not responsible for this. So.
Part of that is because when I was asked to say something, my first question back to Scenic is, did I have to say something nice? I won't tell you what they told me, but I decided to come anyway. So I met Ken, I guess it would have been in 1998, as the Scenic was just coming together and we were building the first sonnet rings. I had left the library at UCLA and moved into dedicated networking work, and there were a lot of moving parts at that period of time. And I think one of the things that would have been consistent about Ken throughout that was trying to balance and doing a very good job of balancing the needs of the Berkeley campus, the UC system as a whole, and the Scenic community as a whole. Because those groups don't always agree on what should happen, and they don't always have the same values or priorities, and making those things work together can be difficult at best. And Ken did a great job of showing how that could happen and how to do the right thing in all cases. And I don't think I have much more, but I do want to note that news of Ken's award has been picked up by Syscon Media and has been reported in Fort Mills, South Carolina, in the Fort Mill Times. I mean, he is well known across the country, and and lastly, his wife was especially thankful about the press release. When she was shown the press release from this morning, she remarked, "Finally, someone has told me what my husband's been up to."
And finally, someone much closer to home at Berkeley, but now with ESNet, Michael Sinatra.
Let me just say that you people are very, very lucky today. Not only are you in the presence of Ken Lindahl, but I have no voice. So you will not have to hear me talk for very long. I do want to say, when I first started working with Ken, actually, I actually first started working with Ken before I worked specifically with him in the same group. I got a job. I'd been basically a Windows administrator, and I started working in Unix and liked it much better. And I got a job with the College of Chemistry. And when somebody, the rumor I heard is when somebody told Ken that I was replacing the Unix guy in the College of Chemistry, he said, "Wow, that's great news." And so it made me feel really good, because it made me feel, number one, that Ken Lindahl didn't hate me, which I had for a long time thought he did. And also made me realize that I might have a career path forward. And I was able to move into the central IT group, and the group that Ken worked in 1999. So I really sort of want to talk about the way in which Ken was very much a mentor to me, and how important I think that is in our field. And I think it's sort of one of those underrated capacities that we don't value as much as maybe we should. We talk a lot about how we're bringing forward the next generation of network engineers. And as I look in the crowd, I see there are quite a few elderly people, not just Ken, but other elderly people as well. And, you know, how do we bring forth the next generation? And there are lots of ways in which organizations like Scenic can do it. There are lots of ways which organizations like Internet2 and Nanog and places like that can do it as well. But I think it's also very important for all of us to, you know, basically follow the example of Ken and being the mentor that he was to me and the other people in my group. And that includes not just telling you how to do something right, but more importantly, telling you how not to do something wrong, and also how to get in your face when you're being a total jerk to your colleagues. And when you get in someone's face and when you don't, when you give them guidance and when you don't, when you let them run with a project and when you tell them, okay, now it's time to make sure that this thing actually works. Our relationship evolved over the years into a point where we were basically equals. And that's another, I think, important factor of mentorship, is when the mentorship relationship evolves into something else, and knowing when that's going to happen. When you bring somebody new in, how much guidance do you have to give them? How much do you have to beat them up to get them to do the right thing? And then when do you let them go? And I think Ken was always had very, very good instincts on how to do that. And it certainly taught me a lot, not only in being a network engineer, but trying to be a mentor to future generations of people. So I think that's really important. And I want to say there are other people in this room. Jim Madden, I remember David Weissek used to always talk about what a great mentor he was. And I know that Nitesh Bandale has mentioned that Mike Van Norman, working with him, was also a very good experience. So not just Ken, there are others of us who've done well, but I think it's great that we recognize Ken for all of his important contributions. Thank you.
So before we call Ken up, I understand that one of the younger members of the audience would like to also make a few comments. So I would invite Jim Warner up.
Thanks, Dave. Scenic was founded in 1996. So I looked through my old emails to find the oldest Ken Lindahl message that I had, and so I'm going to pull one sentence completely out of context and read that. It's this is from 1992, July of 1992. I am the Apple Talk Network number czar, and there are actually two things you can get from that. One is that's the answer to the question of what was Ken Lindahl before he was the network guy, and the answer is he was the Apple Talk guy. And the other one is, you have to see the email, but the A and the T in Apple Talk are both capitalized. So this was before the caps lock key broke on Ken's keyboard. Ken has given us a tremendous amount of both leadership and also lots of art. His network diagrams are legendary. They're not only great network designs, but also a nice thing to look at. And so I thought that it would be appropriate to honor that by taking one of his network diagrams and memorializing it. And if I reach into the right place here, and I'll just show this here and then leave it here on the podium next to the award. So thank you.
Thank you, everyone who spoke. And so now I'd like to call up Ken. I do want to point out that Ken's award is unique in more than one way. First, we'll notice the different color. But if one knew Ken, shift did not happen around Ken. And so his name is properly spelled in all lowercase on the award. And I still want to know if that's the reason the Scenic logo is in lowercase. I haven't quite connected that yet, but Ken? Congratulations, and thank you.
Good enough, thank you. Well, thank you, Dave, and John, Mike, and Skippy. Those words were really too kind. Yeah, it's Dave commented earlier that somebody commented I've moved on to a better place. Kinda. Those of you who know me know that I retired last July, and as Brian said, I came crawling back to the meeting this one last time to receive this award. I don't know that it's really a better place, but I'm certainly enjoying it. My work with Scenic was tremendous. I had a great time. As you can probably tell, I met a great bunch of people, and there's a lot more of you in the audience here today, as well as perhaps listening from home. It was really quite rewarding. It was quite educational as well. And if I could say something a little bit serious, I had the joy and pleasure and displeasure at times of managing Berkeley's connection to the outside world from the early 1990s all the way through 2012, when I basically announced my retirement and moved on. During that time, we went from 2 T1s to today 4 by 10 gig E. That's a more than 10K magnification of bandwidth. And while it's true that the industry has evolved rather quickly, and it's true that everyone else in this room has experienced similar bandwidth increases, or many of us have, still, I don't think it would have been as fast, I don't think it would have been as easy, and there's no way in the world it would have been as affordable as it was. If you heard Michael Sinatra's talk yesterday on slide 8, he had the graph where everything went up and to the right. Well, for us, the cost went down and to the right. Berkeley today has so much more bandwidth, it has full redundancy, and we're paying a fraction of what we were paying in those early days. And I think that's true for a lot of us in the audience. What I want to pull out of this is Scenic has really, really benefited our community. It's helped build the community, and we are doing much better because of it. And I think it's a real treasure. I think those of us who are here demonstrate that we think it's a real treasure by being in the room. And I hope that we take that back to our communities back home. And I would encourage you all to continue to stay involved with Scenic and with the CalRen networks. They really are significant to education in California. And I'll close with that. Thanks.
Well, I'd like to take a moment to, again, congratulate all of our networking award winners. So please join me in another round of applause for them. We're going to go ahead and move directly into the next portion of the conference, which is one of my favorite parts about being here and just learning about all the amazing things that have been going on that have leveraged the network and all that Scenic has been able to do through CalRen, and as you'll start to hear, that affects applications and everyone from around the world. I do want to remind folks that the session is being streamed live during the question and answer period. Please raise your hand if you have a question, and we'll make sure we get a microphone brought to you so that we can have that question aired so everyone watching online can hear as well. And we'll go ahead and start with the iLabs presentation on the remote online lab network. I'm going to invite Kemi Jonah up. He is a research professor of learning sciences and computer science at Northwestern University and director of the Office of STEM Education Partnerships, where he leads research and development projects in STEM curriculum design, cyber learning, online and blended learning models, and web-based patient education and outreach. So, Kemi, the floor is yours.
Well, thank you. It's really a pleasure to have left snowy Chicago behind to bask in some California sunshine. And I wanted to start first by just thanking Scenic generally, and Sherilyn and Louis and Stephanie and the rest of my friends who have really been supporting this effort since it was really just kind of a prototype idea, and really like the preceding comments we've heard, I think a real testament to how the organization really stuck with and believed in this idea to reach where we are today. So I just, you know, when you ask a professor to come up and say a few words, it always turns into a talk, and I'll try to keep it as brief as I can. But I just thought I would take a few minutes today just to answer some of the basic questions. A lot of people, when they hear about remote labs, they go, you know, what are you talking about? What is that? You know, is that some kind of cool simulation or whatever? And so I just thought I would, you know, answer a few of those questions and walk people through and share a little bit about the work that we've done so far and where I think we're headed. And so really, what are remote labs? And I think the best way to answer that in the most fun way, especially since we're at a Scenic conference, is to actually show you what a remote lab is. And I want to do that by sharing one of the new labs that we're working on, which is an X-ray powder diffraction lab. Here's a picture of it here. I don't know that much about it, the science behind it, but I can tell you that scientists do use it to identify unknown crystalline materials and also measure sample purity. So if you've got some kind of inorganic compound and you're not sure what it is, you drop it in this thing and it gives you some readouts of that. So this is really what the iLab experience looks like from the perspective of a student. And we've really worked hard to make this accessible to your average middle or high school student and teacher. So we've you know, really tried to clean up the interface. On the right side here, it's a little bit obscured, is actually a live webcam stream of the device. Actually, it looks like I have to move it over a little bit here. I'm sorry. There we go. At Northwestern, this is the first lab that we've connected at our own campus. We've been working with labs from other campuses, which is sort of a signature piece of the remote lab experience. So let me just walk you through really quickly what this is like. The student, you know, has a chance to ask different questions about it. And then is prompted to enter their research question. I'm not going to actually try to type while I talk. All of this gets saved on the server and then it gets spit out at the end as a lab report that they can then use for their class. And so this is really where the fun part comes. So remote labs, unlike simulations, allow you to actually connect to this device that we're looking at, design the experiment that you would want to run, and then get the data back for analysis. And so really it's at the heart of what we were trying to teach our students around scientific inquiry. Unfortunately, the way that school is set up, and many of you can think back to your high school days and maybe even your undergraduate days, you really had one shot at a lab. You got set up, you had to run through it, you tried to get the same answer everybody else in the room, in the classroom had, and if you didn't, you started to panic, and then that was it. And if it didn't work, you were kind of screwed because you didn't have another shot at it. And we all know, of course, that that's not at all what scientists do for a living. Unfortunately, we're giving kids a very kind of opposite image of what science is like. And so, so here again, you have an actual chance to kind of think about how you want to design the experiment yourself by picking the initial degrees that you're going to measure these X-ray diffractions coming off of, the final one, and then I'm just going to pick some random step size here and try to kind of hurry this thing up as best as I can. And then once you do that, your lab gets queued up and sent over to the device, which is what's happening right now. And we'll see if we can watch it move around. If there are other students using it, you'll be in the queue behind them. And you can log off and come back and get your data later. You don't have to stay online. You can see it now sort of scooching around to our 30-degree start thing. And now it's going to go actually probably more quickly than is scientifically useful up through the different angles that we put in there. Collect the data, and again, I can be sitting here watching it, or I can go and get a coffee at the coffee stand next door here, and come back and do it. And if the results are garbagey, then I have a chance to do it again. So it's really about as close as you can get to to what a real lab looks like. I'm going to let it keep running in just an interest of time. Switch back. Well, it looks like it might be getting close to done. And just give you a sneak preview. So this is, a version of what comes back, and as you go through the different angles, it'll pick up the peaks that are sort of a signature pattern of different materials. And so by working with that kind of reference, you can kind of figure out, what kind of substance is in here. And we get, students a chance at the high school level to use a very high-end, multi-$100,000 piece of equipment. Of course, one that also has X-rays in it, so we're not really going to let them mess around with it in the classroom and have a first-hand experience in using it. This is one of several labs that we're working on. Another one that's coming online hopefully in the next few months is a water quality device in Thompson Rivers University out in British Columbia, which analyzes total organic compound, carbon or nitrogen in your water sample. We've done some MIT started this effort many years ago and has some electronics devices you can use, kind of a custom-built electromagnetism experiment. And I think the granddaddy of them all is you can actually run experiments on MIT's nuclear reactor and play around with a neutron beam that's coming out of it. So that's pretty cool, too. You don't get to do that most days in high school. There's sort of a theme, like all this stuff has to do with radiation and other things you just definitely wouldn't want kids to be playing with. They come home from school glowing. So another question that I often get when people ask me about this is, are they scalable? And I think we're still very early, so I can't answer that question definitively. The lab that we've been working on the longest is a Geiger counter lab that's actually housed at the University of Queensland in Australia. So you can see the radiation theme continues here. And the kids get to measure radiation intensity from a sample of strontium-90, another thing that you're not going to really be playing with in a high school classroom. And so since 2009, when we started this, we've had some fairly steady growth in our user registrations. We're up to just under 6,000 now. And we haven't really been sort of aggressively marketing. It's just been sort of very organic, word of mouth kind of growth. So we've been very pleased with that. It's certainly not the hockey stick that that you might see in other technologies. And if you look at the number of experiments that are actually run on that Geiger counter, we're right up at the 8,000 number. And if you did the math on that, that's about equivalent to running that lab, 8 periods a day in high school for over a whole school year straight. So you can see that students are obviously getting a lot of experience and a lot of time on using this device, more so than you would normally get if you did it by hand. This is a little bit out of date, but you can see we're picking up users really from across the world. Obviously, U.S. is the largest, but really pleased to see folks around the world picking this up. Again, as you would expect, by quote-unquote flipping, you've heard about flipping the classroom with Khan Academy. This is sort of flipping the laboratory. We can move the laboratory experience outside of the class period and outside those limitations. And you can see this is in Central Time, from midnight, again, all the way down to 11 p.m. The students really are taking advantage of it in a broad swath of the day, which is really exciting to see. Even some kids at 2, 3 in the morning are hitting the thing. In terms of scalability, I think one of the best examples and proof points is the University of Technology Sydney. They've actually moved almost their entire undergraduate engineering experience to a remote lab. And so this is their remote lab facility where they've got this green beam that they deflect to measure the stresses on it. And they just have one after the other of these what they call rigs set up, so they can accommodate, just like a server room would in a cloud computing facility, multiple students hitting it with no wait time. And on the back of these are actually another set, so you've got a whole 8 or 16 of them all sitting there as well. So that's really kind of a vision of the future of what this eventually will look like as we scale up. So the other question I get, and especially because I work in the arena of K-12 education, everybody always wants to know, well, are they effective? And we've really spent a fair amount of time trying to understand and document how these work. So, as you'd expect, you can't even get a ticket to the dance without proving that the kids are learning something. And so we did show that they're learning that. But more interesting, at least to me, is that giving students the opportunity to run the lab multiple times actually results in better experimental designs and better research questions, which isn't really a shocker, except that we actually showed that once you open the door to that, it actually works. And the more iterations they do of the lab, the better they get at doing science, which is really kind of the whole idea. Furthermore, as I was saying before, by providing access out of class time, a lot of our teachers still want to do the lab in class because they're really nervous about turning the kids loose, or sometimes they're worried that they don't have access at home in some of our urban schools. But for those kids that do it at home, first of all, we saw that their experimental designs were better than the kids that did it in class. And 3 times more students ran the lab above and beyond the minimal required assignment. So they were assigned to do it twice, and the kids that were doing it at home just voluntarily started running it a lot more than was minimally assigned, which is a good sign that they're intrigued and motivated by it, and 2, they're interested to keep running it, and in fact do run it again. So just the fact that you can run it doesn't mean that they will, but we are seeing that they actually will do it. And we did another little study in the lab here at Northwestern where we asked the quote-unquote subjects to come back in, and we gave them a follow-up test, and sure enough, they actually remembered the material better than someone who used a simulation. So all that's very encouraging, and it's kind of just like the groundwork that we have to lay in order to kind of be taken seriously. One of the other major questions that I get a lot is like, why not just do simulations? And simulations I think are fantastic and they're very powerful. And so we've tried to look at what's the difference. When would you want to use one? When would you want to do the other? Are there students perceiving them differently and reacting differently to them? So we ran a side-by-side study with the Geiger counter lab that I showed you, where we used exactly the same interface, but we yanked out the remote lab and actually put a simulation in there, so the data that you got back came out of the simulator and not out of the actual device. And we found a bunch of interesting things. First, the students who did the remote lab were more likely to feel as though they did a real experiment. So it was perceived as more realistic to them. They liked being able to control the experiment, like what we just did with the X-ray diffraction. We asked the students, which one would you want to do again if you had the choice, and very few of the ones who did the remote lab would choose to do the simulation, except the other way they would choose. The simulation users preferred to do the remote lab if they had another chance at it. And finally, those who did the remote lab would not want, if they were given a simulation, wouldn't really feel compelled to run it multiple times, whereas simulation users, when asked about the other condition, said that they would want to run a remote lab over and over again. And that's exactly the kind of behavior that we want to instill in our students in terms of becoming the future scientists and engineers, which is you want to run your lab again because you got to check your data and make sure that what you got was right. So a technology that affords that kind of desire or behavior is something that I think is really exciting and is interestingly different than a simulation, which kind of caught us by surprise. Because again, remember the interface was exactly the same, so it looked the same. It, roughly gave you the same data back, but the perception that you were controlling something real, some real instrument, turned out to be a lot more important than just sort of the objective facts of the experience. So that was really interesting. And so stepping back, remote labs are really just one element of a growing toolbox of cyber learning tools for STEM education. And most of these are just built on top of the kinds of scientific cyber infrastructure that CNIC and other similar organizations are helping to enable these days. And the list goes on, and keeps growing every time I give the talk, which is really exciting. But that's the space that we're sitting in. And I think the important point isn't which one is better than the other one, or which one of these is better or worse than a hands-on experience, but really to think of it as a toolbox that we can deploy and to be thinking about when do we want to use which tool for which subject area and which grade level and which set of learning goals. And I think if we can get the field towards asking the question in that way rather than having these sort of religious arguments about simulations or hands-on or remote labs, which is sort of where we're stuck right now, I think we'll all be better off and we'll really be advancing STEM learning for the future scientists of the world. Another thing that I think is important to point out is that the cyber learning tools have other very nice features. Regardless of which of the ones on that list you pick, for the most part, when they're used correctly, these tools can provide a more personalized and more authentic learning experience for every student. And that is something that you hear these days when you hear about blended learning or online learning, is that really the effort is to try to personalize that experience so each student is getting exactly the experience that is most optimal for their learning. And when you think about laboratory experiences, often that is the traditional sort of group work where we all know that one or two students in the group kind of does all the work and everybody else is just along for the ride. I have high school kids, so I know this is actually true in practice. And they come home and complain about how the leader wasn't really doing it right and they got a bad grade. So the personalization, I think, is really, really key. The second one is that it again can support that more independent scientific inquiry and from an engineering perspective, that design, test, and debug cycle that we know again is super critical. And being able to do that yourself at your own speed, make your own mistakes, not feel embarrassed about it, all that is critical, again, regardless of whether you're using remote labs or any one of these other tools. And as I was talking to Stephanie about earlier, the next generation science standards, which if you're not in K-12, you may not have heard about, but all the rest of us are kind of flipping out about it, really puts an emphasis on scientific practices. We're finally getting away, and those of you who have kids and looked at what their tests and quizzes look like when they come home, which is just vocabulary memorization, we're finally getting away from that garbage and that mile-wide, inch-deep approach to science to really getting kids to do science. And so all of these cyber learning tools, I think, are really essential and will become even more in demand by teachers when they are trying to implement these new standards and they have to have kids do science. And so it's a lot easier to do that when you've got some computer help. So that's all the good news. There are a couple of notes of caution as well as with any story. Computational tools in cyber infrastructure have really transformed just about every single scientific and engineering field. This is our kind of cool visualization studio where you can sort of do protein fly-throughs, where researchers use to kind of study the structure and the protein folding. But unfortunately, K through 16 largely is still stuck in a very hands-on mindset. That's really pretty much where everybody is, and they're very nervous about leaving that, or in fact antagonistic about leaving it. And so there's kind of a big disconnect between what we all do and the research that we help enable scientists to do in terms of the computational work, the cyber infrastructure work, and what we're still sort of lagging behind in the K through 16 arena. So some of those challenges that I think we still have to address to make this work. First, teacher preparation is absolutely key. We really have to help the teachers master these new technologies and tools. We may sit down and work with them day in and day out, but these are often brand new things for teachers. The work that I showed you really made a big effort to make that interface sort of age appropriate and provide materials around it for the teachers. And those are both really critical if we're going to see success, again, in the K through 12 arena, even through the K through 16. We need more of these labs available. I showed you a few examples, but that's hardly enough to even run one full year of physics or one full year of biology or chemistry. So until we reach sort of a critical mass, it's going to be slow going to get broader adoption. And so anything we can do to increase the number of labs that are available and other tools, all the cyber learning tools, I think is essential. Finally, and this is sort of shocking, there's, well, not that shocking. I mean, there's still some policy barriers in place that really are holding back the adoption of the whole range of cyber learning tools, including remote labs. In one of the examples, in fact, is the UC system is still will not accept an online science course unless it has a hands-on wet lab component, which means that some students will have to get in the car and drive 100 miles or so to get to one of those facilities. And so that policy is still on the books on this campus, actually. So, the takeaway here really is that, we have to try to address these challenges because ultimately exposure to these cyber-enabled tools is going to be essential in preparing our future scientists and future engineers to drive that next generation of discovery and innovation on the platforms that CNIC and others are building. So with that, I just want to kind of tell you a little bit about where we're headed. First, we're going to continue to drive greater access and greater sharing, trying to level the playing field for all students regardless of their zip code. So if you're a student in the East Bay, you should be able to get access to the best instruments that MIT or Northwestern or the UC system has to offer. We'd like to make those professional caliber instruments available, not just to K-12, but also to undergrads as well, because frankly, most faculty don't want to let the undergrads in their labs either to use those devices. And I think most interestingly, it enables the sharing of equipment and facilities among universities, between universities and K-12, which is an interesting partnership model, and also between countries like the Large Hadron Collider and the large community of physicists that use that device across international boundaries. As I mentioned, we're going to continue to drive forward by personalizing the laboratory experience, and we're going to be building out some learning analytics and assessments that help analyze for the teacher what kind of experience the students are having. Are they struggling, and if so, who's struggling? Again, because they're doing the laboratory or the experimental design on our site, it's easier for us to run that data and figure out what's going on and help the teacher make sense of the science learning that's happening. We've begun to work on some mobile interfaces so that kids on iPhone or an Android device, especially in developing countries where that is the predominant mode of internet access, can log on and run an experiment right from their tablet or their handheld device. And finally, and this is sort of a head scratcher, we've all been seeing this explosion of MOOCs, of massively open online courses, but yet we don't really know how that will work for a laboratory science class, and I think that this remote lab technology may be one key to making that work in a MOOC environment. So with that, I just want to again thank you both for the award and the recognition as well as your time today, and I want to acknowledge the funders who have supported this work, and again, thank you for your time. Well, thank you.
Thank you again. This stuff never ceases to amaze me. I don't know if any of you are like me, but it makes me wish that I could just go back in time and be in kindergarten all over again and start going through with all the stuff that's available now. Having been a nerd growing up, I just imagine how much nerdier I could have been. Well, this has actually never happened before at one of these conferences that I can recall, that we're actually ahead of schedule. Now, normally that would not be a problem. However, we do have another presentation that's going to be coming in via video conference. So we're going to switch things up a bit. And I'm going to introduce Linda Rosewood to come up and talk about the University of Santa Cruz Cancer Genomics Hub project. And it's actually really a great privilege for me to introduce Linda, because she and I have had a chance to work together for the last 6 years, and I have always enjoyed her presentations. And when she left ITS to go work on this amazing project, I thought I might never get to see one of her presentations again, and here she is, lo and behold. So she's currently the director of the Cancer Genomics Hub program at University of California, Santa Cruz, and her background is in IT management, network operations, and leading organizational change. So Linda, come on up.
Let's pause for an AV experiment. See if this works. Yes? No? Here we are. All right, well, the CGHUB is sort of a startup. And if any of you have ever worked for something like that, you know how you keep your head down and you're focused on the next week's report and you're working on the next release and you work very hard for months and months and months, and then to suddenly be surprised with an award from CNIC was quite delightful. And I've known about CNIC for the whole time that I've been working at UCSC, and I appreciate very much that you not only recognized our work, but that you provided to us the amazing network that we get to use, for as far as I'm concerned, for free. And that's really wonderful. All right, so yes, I'm Linda Rosewood. I'm the program director of the Cancer Genomics Hub. It is led by David Hausler, as you heard earlier. Let me just start this way. For the last 50 years, our life has been completely transformed by the actual implementation of Moore's Law, and as predicted, computers became smaller and faster and cheaper. And we were sort of able to see that predicted in a graph format. A little bit more than 10 years ago, the Human Genome Project finished, and the world's first sequenced human genome was released to the public by David Hausler at Santa Cruz. And sequencing that one human genome one time cost more than $100 million. So if you put Moore's Law against the lowering price of genome sequencing since the first one was done, by the end of this year, any one of us can have our own human genome sequenced for only $1,000. So as you can see, we think that this is going to be even more disruptive and more transformative to our lives than even the computer revolution. We are, as David likes to tell us, at the dawn of an age of personalized medicine. And personalized medicine is going to be all about personal genomics. And our personal genomics are going to be led by cancer genomics in particular, and here's why. Cancer is fatal, it's serious, and to treat cancer is very expensive, sequencing relatively cheap. Cancer is a genetic disease. It's caused by highly individual mutations in each of our own genomes. Already we have gene therapy that can target the malfunction of certain genes, so we're already moving in that direction. But often the standard care fails, and so people are open to being part of experimental clinical trials. And then finally, with cancer, you don't have to fix the cancerous tissue. You just have to kill it. That's an advantage. So let's imagine for a moment what a cancer consult might look like in the future. Let's say I had cancer. I would have various tissues of my body sequenced, and the sequence just becomes information. As far as CGHUB is concerned, genetics is just terabytes to us. So all that data gets sent up to a very large database where the things that went wrong in my body could be compared to thousands, 10,000, millions of people who also had cancer that may or may not have been similar and may or may not be the sort of person that I am. And then my doctor, my oncologist, can compare what went wrong with my body with what went wrong with other people, and also look at effective treatments that have been shown to be effective for that particular thing. And that's the future of cancer genomics. That's what cancer treatment's going to look like. And I think I do remember a couple of statistics about this. I think 1.6 million people are diagnosed with cancer every year in the United States. And that kind of works out to be 4 out of 10 people under the age of 65 will get cancer sometime in their lifetime. So not only is this work very interesting and from an IT perspective and intellectually, but it touches everybody. So that said, cancer is a little complicated, and here's a couple of ways that it is. Although that there are drugs that target certain mutations, if I had cancer and there was a tumor inside me, different cells inside that tumor would all have different genomes. And so you can select tissue from different parts of a person's body and sequence those cells, and they actually do have different variations. And as you can tell, if you have billions and billions of cancer cells, perhaps one drug may work for a while, but then get overrun by mutations elsewhere, that's going on elsewhere in your body. And so we think that in the future, cancer treatments will be a cocktail of drugs, similarly to how we treat AIDS. And then, like I said, it's not just a matter of one sequence. There's gigabytes and gigabytes of information that need to be collected to understand what's going on with somebody. And then finally, and as Doug inferred, I'm kind of new to this whole area of bioinformatics, so I didn't realize how noisy a DNA sequence really is, or how that sequenced file. That sometimes we might be looking at a variant in the genome, but it's unclear if that is really what happened in someone's body, or if it's an artifact of the sequencing process. And that's why we need lots of data together to be comparing lots of different sequences to see, does that variant show up under what conditions? And as I've been getting to, that's why statistical analysis is key to understanding what's going on with cancer and how to treat it. That we have to achieve the power of statistical analysis to make sure that everybody, all of this data that everyone is paying for to be sequenced is put into one place so that everyone can look at it from different directions. And we need to establish a culture of collaboration among places that are doing genome sequencing, cancer genomics, so that we remove all the barriers to getting the data into one place. And then finally, it's not just the genomic information that's critical, it's the metadata about the person who grew the cancer and about the machines that sequence the files and the tissues. All of the metadata that rides on top is just as important as the genetics information. Now, anyone who has ever tried to share, anyone who's been to kindergarten knows that there are obstacles to sharing. One of the things is that, how we do things around here sometimes people have different understanding of what those protocols are, and it takes negotiation over time to not freak each other out about the assumptions that you've made about how you do things. As it's technical, it's often cultural. There's often policies that have to be worked out, especially when you're dealing with access to personal medical information. As I mentioned, metadata, it's very important, it's very complicated, it's often wrong, and you need to work out what that structure is, how you're going to talk about stuff, and then what the valid values are going to be allowed in that schema. And that, again, needs to be negotiated. You need to go, and then when it's wrong, you need to figure out, well, who has to fix it? And Again, these are obstacles to sharing. And then finally, just what CNIC has been dealing with since 1998 or whenever we started, just the cost of putting data in one place and the cost of maintaining the networks that allow people to get access to that. So what you need is a hub, a place where everyone can put their stuff and everyone can get their stuff out. Once you start that sharing process, then the problems, the obstacles to sharing and collaboration get surfaced, and you work it out. And that is what the Cancer Genomics Hub is. It's a place for us to just get started with this collaboration. So our goals are to receive data from sequencing centers, put it into one place so that people can query it and slice and dice it and take a look at what they need, and then efficiently download it. And analyze it. And then beyond the analysis centers, eventually to be able to work it out so that clinicians and other people could have access to it. Another big part of our mission is that we are not just a repository, that delivering very good technical support to our user community is critical, because if people can't get to it easily, then it'll just be a waste of money. So we do provide, I think, excellent and very personal support to our end users. And then finally, we are facilitating the adoption of standards and facilitating the adoption of API and just thinking about having interfaces between systems as APIs and showing people how well that works. In particular, the Cancer Genomics Hub is a contract with the federal government, the National Cancer Institute, and there are 3 studies from the NCI that we are going to be storing their information. The first one is the Cancer Genome Atlas, which is 25 different cancers and 1,000 genomes of each one. And this is the first time that that much cancer information about all that variety of cancers will ever be available in one place. And then later and we are already storing TCGA data. And then later this year, we're going to be making available 2 more studies from the NCI. One is referred to as Target, which is childhood cancers, and the other one, the CGCI, among other things, includes cancers related to HIV. So this is to give you a picture of what the geographic distribution of this community is. These are the sequencing centers of the TCGA. These are the people who are producing the data that CGHUB is storing. And these are the analysis centers. And as you can see, if you had tried to share data amongst all those people without a hub, that it quickly would become quite complicated. So that's why the Cancer Genomics Hub is the place where the sequencing centers upload, analysis centers download. And the CGHUB is in San Diego, just up the street. Chris Wilkes and I went and gave them all a kiss yesterday, and it was very nice to see our systems there in that very nice data center. But our offices are in Santa Cruz. Why are we in Santa Cruz? First of all, and I guess I'm saying this as an alumni, Santa Cruz has a tradition of collaboration and interdisciplinary research for the last 50 years. That's what Santa Cruz has really emphasized in all of its endeavors. And then also, in the mid-1980s, our chancellor, Robert Sinsheimer, conducted a workshop of leading biologists of the day and to discuss what would a big science project look like in biology. And that actually initiated the Human Genome Project. And it was his vision that got that started. And then near the end of the Human Genome Project, Professor David Hausler at Santa Cruz and members of his team, they sequenced a human genome using a public process and then released that human genome to the public for the very first time, I think in 2000, 2001. Jim and I were there. Oh, Jim's looking at his computer, so okay. I think that, I guess I'm just going to say it, that I think David Hausler has collaboration in his DNA, and he inspires other people to be collaborative like that. So David he's the director of the Center for Biomolecular Science and Engineering, and it was the CBSE, it was out of the CBSE that the Cancer Genomics Hub grew. And because we come out of that community and that expertise, we have a very close relationship globally with the entire bioinformatics community, and it's a good, trusted relationship on both sides. And then finally, just being part of UC, we have access to public resources like Scenic and like the SDSC here in San Diego, and they're very excellent pricing opportunities for us. So here's a picture of our cage, and in the SDSC. It was designed to hold 5 petabytes, and it's scalable to 20. We used standard off-the-shelf hardware. We have 2 of everything. We use CentOS and other standard Linux tool to manage it. One of the few commercial software packages we purchased is from IBM, the GPFS General Parallel File System, which is optimized for clusters and large data sets. Dual RAID 6 arrays, and then lots and lots of co-location opportunities for people that want to do analysis right next to the data. Last year, more than 400 files were downloaded, which added up to 6 petabytes. We're currently holding 400, it's probably more than this now because we get more every day, but more than 400 terabytes of data on 33,000 files. And typically, our users get 2 to 3 gigabits per second downloads. We took a look at what people were looking at last year. I'm not enough of a medical scientist to understand or to make any interpretation of is this what is going on in cancer science today, but these are the files that were downloaded last year. And then I thought I would just grab a typical week last week of what our the outbound traffic from our firewall looked like, and I noticed that someone had a 5 gigabit peak. I'm not sure if this is the first time that this has happened, but it is unusual, but it's sort of significant. It's nice to see. So let me speak a little bit about how people are getting this rate and what they use to download, because I think this is one of the most interesting parts of the Cancer Genomics Hub. The users, both uploaders and downloaders, use an application, a free open source application called GeneTorrent that's built on BitTorrent. And BitTorrent was designed exactly for this use, to sling around big piles of data from one place to another over networks that you can't control. It is widely used all over the internet. It's really robust. It restarts if it drops. And the GeneTorrent, which was developed by a company called Anai Systems, has even more features built around the BitTorrent protocol specifically to help the genomics community. And particularly, it's encrypted end-to-end, which was very important. And then just recently, we ported it to a whole bunch of new Linux platforms and Mac and Windows. On the inside of CGHUB, we run software that we license from Anai, and this is one of the key pieces that is lowering the bar to collaboration, some of those obstacles to collaboration that I talked about before. There's 3 different places where a lot of the problems have been solved. The sequencing happens in a very automated fashion. The analysis happens in a very automated fashion, and the Genos system operates with the pipelines at either end, so that they don't have to, it's not automatically connected, but the application does interface with these automated pipelines. And then also writing on top of slinging the data around, there also has to be interoperability with the data management systems for the metadata. And that happens as part of the Genos system. And then finally, the NCI controls the authentication to get access to CGHUB data, and that's all happens through in common, and that's part of the Genos system. So that has been very successful. So other things that we did last year as part of our success is that we did build the system physically in San Diego. We rolled out, I think, about 5 or 6 enhancements to Genos and the GeneTorrent client. A lot of the features that they added last year were at our request. We are an NIH trusted partner, which means that we are entrusted with the nation's cancer genomic data, which is quite an honor, and it was very difficult to achieve that kind of security authorization. We started the TCGA downloads in January. We started the uploads the month later. And then late in the year, we were able to release the Cancer Cell Line Encyclopedia. And these are real cancer genomes that you don't need to be authorized to use. Anyone can download them and use them. So what this means is that if you wanted to teach students how to do cancer genome analysis, you can download the GeneTorrent client from CGHUB, you can download real cancer genomes, and you can use real genome analysis tools that are freely available in many different platforms, and the students are able to use the exactly same tools that researchers use. Next year, we're going to add more data, as I talked about the childhood cancers and the CGCI studies. And we may also be able to do some greater work with compression, so that even if we stay at 5 petabytes, what we can fit into that 5 petabyte bag may actually be even more information. So let me talk a little bit about where this is going, because I said that CGHUB was a pioneering repository. CGHUB is 5 petabytes. It's 50,000 files probably, and the emphasis is on collaboration and the adoption of standards. But going forward, there's going to be another hub, probably this time in a cloud, that will combine not just collaboration and standards, but also there'll be some kind of compute resources affiliated with it. And that's going to be 1 million genomes, and that's going to be more like 50 petabytes of data. And then we're really going to be able to see the statistical power of genomics analysis. And then after that, in David's vision, of course, then we see, a global network of hubs of this size. And that is where that cancer consult that I tried to paint for you at the beginning of the talk, that's where your doctor will really be able to tap into the information that's available and the experiences and the clinical trials of people all over the world to be able to treat cancer. And this is the amazing team I work with. I'm not sure if there is an adverb that exists that could actually describe how well we work together, but it's really a wonderful team of people. And these are the people who made the CGHUB possible at Santa Cruz, including our management team at the NCI and the SAIC Frederick, who is the NCI's prime contractor. And this is how to get in touch with us. Does anyone have any questions for me? Thank you. Yes, Jim?
A lot of medicine is paid for by the insurance establishment, and as this gets bigger, it's going to get more expensive, and so at some point the funding has to shift away from the government, or I think it has to shift away from the government, and be picked up as part of regular healthcare costs. Is there any roadmap for how that kind of transition happens?
Not that has been told to me. I'm sorry.
This is really extraordinary. It's Larry Smarr.
Yes.
Really extraordinary what you've done, and I love the cyber infrastructure architecture that you've built, because using things like SDSC makes it possible for other people to imagine adding to that. One of the questions I had is whether you're looking at all in the microbiome and its relationship to cancer, or is it just the cancer and human cell genomics?
I think that's very interesting, because the more I hear about the microbiome, which is the colony of other things that are not human that live inside of us, is actually 10 times more than the human cells. I don't know if you guys have heard that yet on Radiolab or something. I think that's really interesting. The Cancer Genomics Hub is just about these 3 studies that the NCI is doing. However, anyone who wanted to do a hub of the genetics of the microbiome would, I think that the things that are working for us, they could start with the architecture and the methods and the protocols that we're using. That's what I mean about this being pioneering. Cancer genomics is leading the way. all the other genomics activities in plants and evolutionary, all of this data sharing, hopefully we can learn from our mistakes and then have more people build on what we've done.
Great, thanks.
Anyone else? Thank you very much.
Thank you. So, yes, I will talk about the Project Adamant. One of the things that I believe we got right first time on this project was the acronym. We actually managed to come up with an interesting interpretation of the word. It stands for Adaptive Data Aware Multi-Domain Application Network Topologies. And I represent a team consisting of 3 institutions. RENCI, Renaissance Computing Institute, part of University of North Carolina at Chapel Hill, Duke University, and the University of Southern California, ISI. So the 3 co-PIs in this project are Eva Dielman from ISI, Jeff Chase from Duke, and Charles Schmidt from RENCI. And on behalf of all of us, I'd like to thank CNIC for giving us this award. I'm sure there were a number of worthy projects that were considered. Unfortunately, I think the slides today came out more technical than I wanted them to be, in part because this is kind of a difficult and complex area to talk about. But in a nutshell, what the project is about is allowing complex distributed scientific applications to provision a variety of computational network and data resources for themselves in such a way that their execution can become more predictable, better isolated, run at high performance, and so on and so forth. So the main problem that we're addressing is that most computational tasks have now become associated with data, sometimes also big data. In the past, these problems have been addressed by creating infrastructures that are dedicated to particular problems. And of course, LHC, LIGO, and other projects come to mind. But we believe that this time, in a way, this time has passed. Introduction of things like cheap DNA sequencers, which cost a few tens of thousands of dollars and can be put in the hands of individual researchers and can produce large amounts of data very rapidly, kind of completely changes the balance of this equation. The complexity of the computational problems associated with the data is, of course, increasing. And most importantly, it is no longer enough to have just a little cluster in the back of your lab to take care of your computational needs. Your tasks, the computational tasks as part of your problem may involve tightly coupled, loosely coupled execution models, and may involve things like MapReduce, need for dedicated hardware like GPUs and other things. And the compute infrastructure underneath these tasks keeps changing because vendors are coming up with better and more interesting solutions that we have to find a way to harness in order to improve the efficiency and the speed of the discovery. So one example of these complex applications that we're considering are called computational workflows. What they do is they express complex computations as essentially directed graphs in which, in the data-driven variety of workflow applications, the data is moved on the edges of the graphs while the nodes represent the computational tasks. And those nodes, in principle, can run on different types of resources and can be separated in time from other nodes. The nice thing about workflows is this is a high-level and portable expression of the execution. And importantly, because you've encoded your computational workflow, it becomes repeatable, and not just by yourself, but potentially by other scientists, and it also improves efficiency. But importantly, because this execution takes place in steps, it also gives the opportunity to manage resources that are running underneath the workflow. And so as part of the Project Adamant, we're looking at a number of science domains that have this combination of data and computation in various proportions. And the reason why we chose these fields was specifically because they offered a diverse set of requirements to us. So one is genomics, which again, I come back to the inexpensive DNA sequencers that are available in manual labs now. What they permit scientists to do now is study entire populations and genetic variations in between them. So this is a very, very big data problem with fairly modest computational needs. However, the data continues changing, continues accumulating. It comes from multiple databases, some maintained by commercial entities, some maintained by open consortia, et cetera, et cetera. And making sense of all this data is a difficult problem. Another domain is astronomy, where we're working with a project called Montage, where astronomers essentially take snapshots of the galactic plane and then stitch them together into one large image. And this is both a data and a computationally intensive problem, and it also lends itself to encoding as a workflow very well. And this is where finding the right computational resources, linking them to the data, and it becomes very important. And finally, we're also looking at earth science as another science domain where basically computational modeling of seismic activity can lead to basically practical solutions to questions like what should be expected in terms of ground motion in a particular location in the next 50 years. And these tasks include both computation, but also a lot of probabilistic modeling. So the interesting thing about this particular domain is that it includes this diverse type of computation where part of it has to be tightly coupled and executed on some type of computational resource where MPI is available. And part of it can be loosely coupled in what we would call pleasantly parallelizable. But these steps need to be linked with each other, and the data needs to flow between those steps in order to achieve the final result. So how can we manage this complexity? Because on the left side of this slide, what we have is workflows and data and maybe some local resources. On the right, we have these national scale resources like Exceed, like the available grids, like the emerging institutional clouds, of which Genie, for instance, could be one example. It could be also public clouds like EC2 or Azure or others. So the problem then becomes of how to manage these computational workflows in concert, managing both the process of computation as well as the process of managing the resources underneath the computation. So you need a lot of capabilities that have to do with planning the workflow, scheduling the resources, properly arranging those resources into connected arrangements so that pieces of these resources can talk to each other. And of course, the goal of it all is providing scalability, higher performance, and reliability. So in this case, the solution for us is to enable the workflow to explicitly figure out and manage the resources that it is running on. And at different times within its execution cycle, a workflow might request resources that are available from grid, sometimes from cloud, sometimes from some special purpose computational resources like a supercomputer. And something needs to orchestrate all of this together in order for this computation to take place. So as a workflow management system, we're using Pegasus, developed at ISI by Eva Dillman and her teammates. And it has a lot of very interesting capabilities already by being coupled with Condor and grids. However, one important aspect of it, and I'm sure you can hardly see it here below, but Pegasus makes use of available resources but cannot control them at present. And part of the tasks that we have put in front of ourselves for Adamant is enabling exactly that, and allowing a workflow management system to explicitly manage its own resources. So how would we want to do this? So the common way of doing it today is through middleware, which to some extent is not the best way of doing things, because middleware not only schedules the resources and connects them together, it also remains as a layer between itself and the application, inserting its own abstractions on the path, which sometimes becomes more of an obstacle for executing an application. Instead, what we'd like to see is some system that creates what we would call a slice of resources for the application. A slice consisting of computational, storage, network resources that link each other from perhaps multiple providers. So you might have some number of institutional clouds lending its resources into the system. You might have backbone providers like ESNet, like CNIC, like NLR, like Internet 2, and potentially linking in public clouds or other institutional resources. And what we would want to do is create a slice in which a workflow can begin its execution. The slice can elastically grow and shrink as the workflow executes. And at the end, release the resources so that multiple such activities could be multiplexed into the infrastructure at the same time. But the important bit here is that Pegasus workflow management system is allowed to do explicit resource provisioning of the system as it executes. So let's look at briefly look at the ecosystem in which the resources can be acquired. Today, really what we're dealing with is what we're calling as network infrastructure as a service. Because what we have is a number of providers who provide a service in which networks can be bandwidth provisioned on demand. This is in contrast to the commodity service that we see today, where essentially you just you connect your network device into the network and you get best effort service. Now you can get some gains out of it by simply increasing the bandwidth. But from our perspective, the important thing is actually intelligently managing this bandwidth by providing on-demand bandwidth between the necessary points of connections into the network, and then releasing those resources when they're no longer needed. And there are examples of systems like this in existence. There's Oscars on ESNet and Internet 2, Sherpa on NLR, and there's NSI, and a number of other systems like this. So we have these backbone providers. We have other types of transit providers, and we also have cloud providers, which provide computational and storage capabilities, typically as a kind of a package with a common API sitting on top of them. And so orchestrating these together such that you can acquire some resources from one provider, more resources from another, link them together with the network, link them to a storage array somewhere else, this is kind of part of what we would like to enable a workflow management system to do. So in this case, what we're showing is, again, a kind of a different way of looking at this slide. At the bottom, we have the computational, the network, the storage resources. At the top, we have the workflow management system. And on the right, we have the system of which an example is a system called Orca, which we've been working on. Orca stands for Open Resource Control Architecture. And it is the workflow management system that speaks to Orca in order to orchestrate the resources. Here, what we're showing is a slice, a very, very simple instantiation of a slice. And the resources from different types from different providers are drawn into the slice for the time that they're needed, and then they're released afterwards. So a few words about Orca. Orca was designed by Jeff Chase at Duke originally, and then for the past several years, ourselves, my group, and his group have been developing it as a Genie control framework software. For those of you who are not familiar with Genie, Genie stands for Global Environment for Network Innovations. It is an ambitious attempt to build kind of network infrastructure as a service for computer science experimentation, where a computer scientist can on demand create a slice of this infrastructure that's gathered from multiple campus and network and providers, run a distributed experiment on this infrastructure, collect the results, save them, store them, and then release the resources so others can use them. So Orca is an example of a control framework that is capable of doing this. What it provides is essentially various types of orchestration services, things like resource brokering, image distribution for compute instances, topology embedding, because when, particularly for applications, it is important for the system to solve some of the problems related to how resources are distributed. Application may have an idea of what its topology might look like, but it may not have an idea of where the topology needs to be embedded, which providers the resources should be acquired from in order to create a slice. There is also things like authorization. Stitching is a process that we refer to, which is a connection of different types of resources to each other in order to create the connected arrangements. And Orca has been developed for a while, as I mentioned, and with funding from Genie, from Department of Energy, and from NSF. And these are some of the systems that Orca is capable of essentially orchestrating together. Again, this is kind of, I'm sure you can't see half the slide, but the details of the slide, but the important thing to take away from it is that by using agents located near the specific providers of different resources, a cloud and maybe some transit networks, Orca is capable of essentially pushing buttons on their native APIs, whatever those happen to be, in order to achieve the orchestration of slices that span the entire range of resources. So this is kind of the background for some of the application work that we're planning to do. But obviously, we need infrastructure in which we want to test these ideas. And where we would like to test them is the testbed we're calling ExoGenie. It is part of the greater Genie environment. And RENC has been funded to build this part. It consists of 14 racks. GPO stands for Genie Project Office, by the way. These are essentially cluster-like racks. The big difference being that their networking is enhanced compared to what you would see in a typical cluster. There are two networking switches, one for essentially network management, and the other is what we call a data plane switch, which typically connects into a layer 2 or an open flow provider. And this is what allows us to create these connected arrangements of resources, not just within one rack, but between such racks and to other non-rack resources. But essentially, each rack is a small cloud. It is based on OpenStack and XCAP, and experimenters can come in and using Orca or Genie interfaces request themselves the resources from these racks, create slices, and then run activities on those slices. And the important distinction here is that unlike middleware approach, Orca does the provisioning and then essentially gets out of the way. It authorizes the creator of the slice to use the resources after they've been provisioned, and then simply keeps track of the fact that the resources need to be released when the researcher or a user said they were going to release them. What does ExoGenie look like today? Again, the slide attempts to show this. So there are a number of racks that are already operational, like Duke, UNC, RENC, BBN in Massachusetts, Florida International University, University of Houston. And the racks that have this light gray background are the ones that are coming next. So there will be a rack at NERSC, there will be a rack at the University of California, Davis, there will be a rack at Starlight, there will be a rack at the University of Florida, Gainesville. And we do, in fact, have a rack in Australia. So we call it, we claim by this, we claim the international collaboration. And they're connected to the variety of network providers, just like I showed you, right? We have essentially representation from Internet 2, from NLR, from ESNet. And the idea is that an experimenter will be able to come in and create slices that consist of resources in each one of these racks, and they can be tied together in a variety of ways. So that's the substrate. And finally, I think we're getting to the final portion of this presentation, and that is, how are these things coming together? So prior to Adamant being funded, and I think I forgot to mention that Adamant is funded through the NSF CCNIE program. But prior to being funded, we've actually performed some amount of work in testing this idea of how workflows could be run on such dynamic infrastructure on these slices. So of course, the first approach was to manually create a slice, launch a workflow, and then see what happens. And this is exactly what's shown in this picture. So you have a workflow, you might have a computer, there's a slice is static, it's created ahead of time, and this is on top. The workflow launches, and it goes through some computational steps, then it ends, but the slice doesn't change throughout the execution. And so essentially you have to plan for the worst case, or else suffer the penalty of performance. And that's not really a great approach. It is existence proof of the fact that this can be done, but nothing more than that. And that's something we tried about 2 years ago. The next step, and this is actually part of our last supercomputing demo, was to allow the slice to grow and shrink as the computational load on it increased or decreased. And so what this shows is you have a miniature slice is created ahead of time, but it doesn't contain all the resources needed. The workflow is started. Part of the workflow is, in fact, requesting more resources from ExoGenie, from Orca, to be created. A computational intensive workflow step occurs on this enlarged slice. then part of the resources are released. Other steps can be executed in a smaller slice, and this process can repeat, of course. This is just a very simplified version of what is being done. Where we're going with Adamant is this picture. So now what we have is compute-intensive as well as data-intensive steps within the workflow. And what we would like to do is enable this dynamic network behavior within the slice, such that the slice can not only grow computational capacity, but it can also grow network capacity by modifying the links wherever possible, for instance, modifying the bandwidth of the links that is available, growing new links to ingest or save data out of the slice, and so on. And all of this is done under the control of the workflow by essentially automatically inserting special steps within the workflow that are responsible for the provisioning of this slice. And this is our near-term goal. And this case shows kind of what we call on-ramps, where a slice needs to either ingest or save an important bit of data from itself. And remember, slices are ephemeral. So if you want to have something, a result that is saved for all eternity, you can't leave it in the slice. You have to save it somewhere. So this step shows how a slice is connected to, for instance, a permanent storage facility to which the results, the data files, whatever the output of the workflow is, are saved for future reuse, and then the rest of the slice can be released. So what is missing in all of this? We're still, the project is very young. We only just started, even though we've done some preliminary work. What we're missing is tools and systems that can integrate in a dynamic way without much human interaction the operation of the workflow-driven applications and the infrastructure. We also are interested in enabling and developing tools to manage workflow ensembles. This is a relatively recent area of development where, for instance, for doing a parameter sweep over a particular interesting computational problem, what you would want to do is not just run one workflow, but you may want to run 100 or 200 or 1,000 of them with slightly varying parameter settings, and then collect the results. So that's referred to as an ensemble. So obviously, the problem of provisioning resources for an ensemble is like the problem of provisioning resources for an individual workflow, except it's quite a bit more complex. So we need to be able to orchestrate the infrastructure in response to the application, to which we have some early results, but obviously we'd like to move quite a bit further. We would like to add monitoring capabilities because it really needs to become a closed feedback loop between the application and the infrastructure. It's not just that the application throws requests out and the infrastructure says give me more capacity. It needs to be able to measure how this increase in capacity actually influencing its performance. It needs to be able to expand and shrink the resource pools in response to the performance demands. And importantly, we have to integrate data movement and storage decisions with workflows and the resource provisioning. So you can imagine a slice that, for instance, acts as a content distribution network for other slices in an intelligent way. And other slices can connect to this slice in order to move their data around. Or it could all happen within a single slice. It's really kind of more of a domain-specific question. We would like to enable both of those scenarios. So in summary, I think what I'd like to say is, Adamant, the primary focus is on data-intensive applications, astronomy, bioinformatics, and earth science. The important takeaway is that it's both management of the workload, which is management of the application of the computation, but also the management of resources and resource provisioning responsible for executing that application. Monitoring and execution, so that is important because adaptation of resources to demand is just as important. And the platform in which we plan to do this is Exogeny plus some resources from grid community, resources from kind of supercomputing sites, etc., etc. And at the bottom, there are a couple of URLs from which you can learn more about this project and others. That's it. And I would like to again thank CNIC for this award and for the opportunity to give this presentation.
We would like to thank you as well, and we do have some time for questions if there are any questions in the audience.
Yes, Mark. I got it. Yeah, thank you very much for your presentation. One of the concerns that I have when we talk about dynamic infrastructures and turning up capacity, in particular, as you mentioned, Oscars on ESNet and Sherp on NLR, there are ports that have to be allocated and dedicated to the edge devices in order to make those available. And as we move to higher speeds, those can still end up being kind of expensive elements as we try to grow the sets of these clusters and the number of interfaces on those clusters. Have you considered that in terms of how that could impact the locations or the number of interfaces for these subclusters like you've got with the Exogeny?
So you're absolutely right. This is an important problem. We actually, my group actually looked at this problem as part of another project funded by DARPA. So obviously, a particular interface has to be provisioned for peak capacity at any given time. However, going through the network, you can take advantage of multiplexing and not always use that peak capacity, in any kind of a point-to-point connection. So yes, the consideration of the available capacity on the interface is already actually part of resource planning that we do, but it obviously will have to become even more sophisticated to account for the issues you mentioned. Also, we would hope that some of the data collected out of this might drive the decision as to how to allocate this, capacity, essentially where to provision those interfaces and to what speed in order to achieve better results.
Thank you.
I noticed in your current system you were using OpenStack, but you did mention things like Amazon and Azure. Do you have plans to try to figure out how to deal with the heterogeneity of all these different cloud computing environments?
Yes, it is not an explicit part of this project. However, we've had a number of related projects that have looked at this. So interestingly enough, EC2 now actually begins to offer a layer 2 connection directly into their cloud. It's kind of a static peering that you have to arrange for. But it is one of the things we're looking at is essentially just another type of on-ramp. If you would like to shift part of your computation to Amazon and you have the money to pay for it, we should be able to throw up an on-ramp from a slice to one of the peering locations and help shift your data into the cloud, because there are numerous publications about the poor quality of networking connections within the Amazon cloud and the public internet.
Thanks.
Okay, any more questions? Well, once again, I'd like to thank you, Ilya, and I'd like to express a thank you to all of our presenters for the award session today.